We already talked about bismaleimide type of resins very briefly. The other types of resins that you have in the composites field, especially for polymer matrix composites, are wine esters, which are typically used in a number of naval applications. You have phenolics for high temperature applications. You have carbon matrix, especially carbon-carbon type of composites for really high temperature applications, especially in the space. You have polyamides and related matrices for intermediate temperatures like 600 to 700 degrees centigrade. You have cyanate esters, which are one of the best space qualified resin matrices. You have polyurethanes and then silicones. These are typically about 30% of the total composites market, but there are some specific and critical applications, like in the case of carbon-carbon, or you have silicon carbide in the case of nuclear applications. So these are composites that you cannot make by any other way, and those critical applications can only be met with these kinds of applications. So what are the important properties for some of these specialty resins? Wine esters, they are one of the resins that have the best moisture resistance and seawater resistance than any other resin system that you can find. So all kinds of naval structures are made with these kinds of materials. But of course, they also have processing issues, but the composites are such that they only can meet those kinds of applications. Then you have flammability. For composites that need good fire resistance, phenolics are the only ones that you can have. But sometimes processing phenolics is a problem, which we will talk about going forward. So what you do is you can have a combination of wine ester and phenolic, or epoxy and phenolic. So if you need fire resistance, you can have the phenolic on the surface. Then for space applications, you have cyanate esters. You have other types of applications where you might have silicones, or they call it dicyclopentadienes or DCPDs. So these are some of the specialty resins. So coming to wine esters. Wine esters have properties that are between unsaturated polyesters and epoxies. The cost is also between unsaturated polyesters and epoxies, but they have superior toughness and corrosion resistance to organic solvents and water. But the processing is an issue because you need additives there that are not the most environmentally friendly type of materials. The curing is like unsaturated polyesters, and then therefore curing is easier than epoxies. So you might be able to do curing at room temperature itself, and then you might have to do post-curing at elevated temperature. So what are the applications of wine esters? Pipes and tanks for the chemical industry, scrubbing towers, marine applications where corrosion resistance, especially to salt water, is extremely critical. But you have to add styrene just like the polyester type of resin systems, which is not the best thing. So more recently, there have been more newer types of wine ester formulations where no styrene contents have been averaged, have been used. But the problem there still is that you have to have curing agent which contains some carcinogenic contents. So again, it's a plus and a minus. So you have to make sure that you address all these issues before these kinds of systems are included into specific applications. So wine luster, the resin systems, the cross-linking mechanism is very much similar to polyesters. I'm not going to go too much into detail about that. And the wine luster is synthesized by reacting epoxy resins with acrylic acid, and it opens up the epoxy ring and it forms new bonds with the oxygen and carbon at the epoxy ring site, the epoxide site, and you create an unsaturated carbon-carbon double bond which becomes attached to the end of the chain. So these are sometimes called acrylic modified epoxies. And if you have a peroxide initiator and styrene, they can be cross-linked just like an unsaturated polyester. So you synthesize that, but anyway, most of the time an end user is not going to be seeing all these synthesis part, but just to give you a flavor of what is going on, I'm just throwing it in here, that's all. So there is a lot of similarity between wine luster backbones and epoxy backbones. And the cross-linking reactions are also pretty similar. And you are creating a free radical reaction and it attacks the carbon-carbon double bond and it breaks and it chains up and links up to create a very long bond. So again, these are some of the reactions. I'm not going to be asking questions about that, but just realize that these are some of the reactions, some of the types of reactions that you will find in wine luster type of resin systems. So what does the peroxide, what does the initiator do? It initiates by splitting into two, which and each of them will contain a free radical, and those free radicals will react with the carbon-carbon double bonds at the end of the wine luster polymer, and then you create a new free radical, and those free radicals then will react with the styrene molecule, and then the styrene and polymer bonds will bond together, and depending upon the ratio of styrene and wine luster, the reaction will proceed. The reaction is pretty fast. You have very fast gel times and pretty low shrinkage. So compared to say phenolic type of resin systems, no byproducts are given out and no shrinkage. Or very little shrinkage. So similar to polyester thermosets, you can also cross-link wine lusters. And just like polyester systems, the optimal concentrations and optimal choice of ingredients can vary. And in this case, the most common initiator is methyl ethyl ketone peroxide, or MEKP. And it's pretty nasty smell. So you got to be extremely careful while you're doing this inside your lab. And there is also an accelerator that is used, and many times it contains cobalt, but it was what it was started with. But nowadays they are all users or manufacturers of wine luster end products are going away from cobalt, and you can also have aromatic amines nowadays that is used as an accelerator. So what are some of the properties? Corrosion resistance is extremely good, and it is less susceptible to chemical attack. And if you see a composite system that is kind of greenish tinge, you can assume that it is wine luster. And the long-term thermal aging and corrosion resistance is far, far, far better. I only said it it here far. It is far, 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 far better than polyesters. Polyesters are not very good at in corrosive environments at all. And it gives you extremely good bonding between the fibers and the resin system. It also leads to higher mechanical properties. It has reasonably good flame retardancy. If you want to make it better, you can have a coating of phenolic, or you can co-inject the phenolic resin along with the wine luster type of resin. But thickeners or things like additives to thicken the resin system do not always perform very well with wine lusters. So in order to increase the cross-linking, what you do is you have to post-cure the part. And or if you use benzyl peroxide and dimethyl aniline, then that also can increase the cross-linking. And or you can dilute the corrosive liquid the part is exposed to, but that is not always possible. So you have to post-cure the part. Or you might also want to operate it at the lowest operating temperature. But the last two bullet points are probably not possible. So what you do is the first two bullet points. So you post-cure and you use benzyl peroxide and dimethyl aniline to do the curing, which increases the curing, the cross-linking ratios. Coming to phenolics, phenolics have got one of the best fire retardancy among resin systems. And these were the first thermosets developed, and they are about 10 to 15% more expensive than polyester thermosets. It is used in the non-reinforced form for electrical switches, junction boxes, etc. But the problem is that it has a byproduct of water, and it also undergoes shrinkage. Weight shrinkage itself is about 15%, and volume shrinkage can be as much as 40% for phenolics. So when you want to make a carbon-carbon composite from a phenolic type of a resin system, you have to do infusion multiple times in order to get the highest densification possible for these composite systems. So in order to avoid that, you add fillers that can be used to reduce the shrinkage and improve the toughness. So some of the fillers that you use are wood flour, sawdust, talc, etc. So by doing that, you can reduce the amount of shrinkage, but still you cannot completely avoid the shrinkage, which is something to note here. The color of phenolics can vary from brown to amber, and that shade of the color is extremely difficult to control that. So sometimes you may want to add some kind of a pigment to make the color uniform. And what is the best way to do that? I add carbon black. Carbon black, as you know, is also an additive to improve the UV resistance of these composite systems or resin systems. So you get black. You can't get anything blacker than black. So that's what you do. Phenolic is also used as a glue in plywood, and there it does not contain a pigment because it is not seen by the consumer. So why add extra pigments and things like that if you don't need it? Okay. So what are some of the major properties of phenolics? The first and foremost property is excellent flammability resistance, low heat transfer, high thermal stability, high electrical resistance. So you use them in junction boxes and things like that. And it also has got fantastic resistance to chlorinated solvents. And it has got very good adhesive properties, so you use that as an adhesive rather than as a composite resin matrix. But the problem with phenolic is that it is extremely difficult to process compared to epoxies. It has got very high resin viscosity, so you can't easily infuse that into a resin matrix or a fiber preform. So what do? You have to use a pre-preg rather than infusion type of a process to make these composite systems where phenolic is a resin matrix. So in order to get good properties, because it is difficult to process, in order to do that, you have a method that was developed by University of Delaware, the Center for Composite Materials at University of Delaware, and the Army Research Lab at Aberdeen. They came up with a technique called co-injection resin transfer molding. You co-inject the resin system into a preform. So the bottom would be the phenolic and the top would be the, no, sorry, the bottom would be the vinyl ester and the top would be the phenolic type of a resin system. So the processing is not that difficult, and the any byproducts that come out can easily be removed from the composite system. So here are some of the additional details about the phenolic system. I'm not going to go too much into detail. It is there if you are interested to go and look into that. So the cross-linking is that it, as I said to you, it can shrink by quite considerable amounts. So let me stop here for this stage and